the things so that we can get going in this course. But welcome to Chem 1402, Chemistry for Health Sciences. Some announcements first off. We're going to talk through attendance for just a second. I know I've mentioned this and it's definitely on the syllabus. So here's what I'll say first thing. If you have not read the syllabus, that's your homework for the weekend. Hop on Blackboard. It's in the syllabus tab on the left and just read over it because there are definitely details you need to know. How to do homework assignments. We already have, don't let this blow your mind because nothing's due tomorrow. But for the rest of the month, we have 3 assignments. 2 are really quick. And then there's our chapter 1 homework assignment. It's all on mastering chemistry. A lot of people have sent emails about I don't have the access code. I think one person today said that the bookstore had emailed them their access code. Has anybody been getting emails? You can raise your hand. I could see. Okay, good. So the access code should be coming in from the bookstore. I checked our mastering course, only about 28 or so students total, and there's like 100 of y'all between the 2 lectures. So make sure you try to get enrolled in our mastering course because the first assignments that are due, and they're just intro assignments, they're like 5 points each, and I think one of them you won't get any points deducted for wrong answers. It's kind of like if you do it, you'll get points for it. So it's just an intro to mastering chemistry and teaches you how to use the site, how to format your answers, and then there's a chemistry primer, which may ask you questions that you are less familiar with, but it's getting your brain kind of back into chemistry language, chemistry topics that we're going to be talking about. So do those assignments. Again, they're 5 points each. And then those are due, I believe, next Wednesday night at midnight. Make sure you read the portion of the syllabus that says homeworks, because if you see something on the syllabus that says it's due September 1st, it's actually due at midnight the night before. Okay. And that's for all assignments. I want it done by the time September 1st rolls around. If you have questions on that, don't hesitate to email me. But once you get on mastering, it tells you the exact due date and time. So that's some assignments. Make sure you pay note of that. That's on 2, what will be your best friend in this course is on the last 2 pages of the syllabus, and we'll look at this in just a second, are the schedules, the lecture schedule and the lab schedule. So if you have not viewed that, that is key because it tells you when everything's due, what reading to be doing, what lecture we're covering when, and what labs we have due every single week. So check out the last 2 pages of the syllabus for those schedules. Okay, attendance. If you haven't read the attendance policy, you get 3 excused absences from these Zoom lectures. And the reason why I want y'all to all be on synchronously live is because one, for me, I know, and for everybody else, it helps us exercise the self-discipline that we're just going to need this semester. Let's be honest, doing everything virtual, we're going to have to be extremely disciplined. So I just decided to make it mandatory, 1, for that reason. 2, if somebody has a question, if I just were to post all these as videos, if you have a question, you can't ask me in the moment, and chances are if somebody has a question, 20 other students have the same question. And so I think that dialogue is critical for this course as we go as much as possible. If you're not too afraid to answer your question. I get it. I've been in big Zoom meetings before and I'm like, I don't want to ask my question. It's stupid. There are no stupid questions. I seriously mean that. So don't hesitate to type it in the chat, unmute yourself and ask me. So on. But with attendances, that 4th absence from lecture, and I do take attendance for every Zoom automatically records attendance for me, and it shows me how many minutes you were on the Zoom meeting. So if you decide to log on for 2 minutes and then hop off and go enjoy your day, I'll see how many minutes you were on. So I'm going to be taking attendance. That 4th, if you miss 4 times starting with the 4th, then I do take points off starting there, just because I think your attendance is critical to your success. With that being said, if you get COVID, if something crazy happens, you're in a car wreck and you have a 4th or a 5th excused absence for a legitimate reason, just communicate with me. Okay. I'm more than happy to work something out. All these lectures will be recorded and I will post the recordings so you can go back and watch them and rewatch them at your own pace. But I am still taking attendance. So just because I'm recording them and posting them, don't take that as a leeway to not show up in our lecture times. All right, that's attendance. Labs, I know everybody's been harping on distance and masks, but we do have our first wet lab next week if you're in Group A. If you're in Group B, you will be doing a dry lab. You will not show up to campus. You will not show up to lab. You will have all week to get that done. I have not posted any due dates for labs yet, and I will send information about when your labs are due. But everything will be turned in electronically. So for the people who are coming in for the wet lab next week, to do the safety and detecting signs of a chemical change, that's the lab we're doing, When you're coming in, you will collect your data. You'll write everything down. I would print out the lab procedure and bring it with you, fill out all your data sheets, post-lab questions, all that. But then you will go home and you will type everything into a Blackboard assignment, okay? And again, I have not even created it yet. I'm gonna do that tomorrow, and I'll communicate when those things are due. So yes, it's like you're writing things down twice, but again, just the colleges are advising that we don't collect things in paper form. So that's the way that'll be handled. If you're doing the dry lab, I encourage you to still print the PDF out, show me all your work, and then you will upload pictures of certain problems and things for the dry lab as well. The due dates for the wet lab and the dry lab may be different times, okay? But there's certain things in the dry lab next week, if you're in lab group B for next week, that we just haven't covered in lecture yet. So that I may give those dry lab people more time to complete that just because we haven't covered it in lecture until next week. So that's lab stuff. Make sure, I sent an email about this yesterday, that our department has a very limited supply of lab goggles. So especially for those of you in the wet labs, you need to go ahead, and I urge you to just purchase them somewhere else if you don't have a pair. Some of you, this isn't your first semester at UCA and you may already have goggles, glasses, great. But our department, they are selling them, but they only have like 150 pairs. So I bet they're going to be sold out by tomorrow. So Amazon, I think you could buy them. Just check the syllabus. On the first page, it tells you what kind of lab glasses or goggles you need. Make sure you get that kind. If you have questions about it, just shoot me an email. What else? There is a video that I sent in an email Monday, and it has logistics about how to enter and exit our building and our lab. And this is all new to me as well. And for most buildings on campus, this is how it is. There's certain staircases that are only up staircases, certain staircases that are only down. You enter certain ways, you exit certain ways. So just check out that video. It's really not long, just so that you even enter Mannion Hall correctly and the lab correctly. And it talks about sanitization and all that in the lab as well. Okay, I think that's most of the announcements that I wanted to talk through. Okay. All right, well, with that being said, I'm gonna share my screen really quick, and we're gonna look at the syllabus schedule for just a minute, and then we're actually gonna jump into our very first lecture. So let me share my screen. Okay. So you guys should be able to see the syllabus now. And here is our lecture schedule. And I just wanted to remind you, you may have already seen this, you may already be up on the game about it if you have your textbook. If you don't worry, you can catch up on any of the readings. But here's our schedule. So we are starting today with this lecture, chapter 1. And I have suggested that you read sections 1.1 through 1.5 for the topics and the stuff we're going to cover today. So please pay attention to this assigned reading column. And it's really only 2 to 3 sections. Sometimes it's 4 or 5, but they're pretty quick. So here's the deal. If you just stay on it, it won't pile up. But if you don't stay on it, it will pile up and seem like a ton of reading. So please do that reading in the textbook as we go. Again, the electronic copy of the textbook is okay with me as well as the hard copy, whatever you prefer. And then you also notice, let me point out this column. This is when your assignments are due. So we will have a quiz next Thursday, or it will be done by next Thursday. I'll probably make it available next Wednesday. But again, I will send emails about, I haven't even written the quiz yet. So this just tells you when you have assignments coming up and when they're due. So notice Intro to Mastering and the Chemistry Primer, they will be due at midnight on August the 26th. I know it says August the 27th here, but I want them completed by that day. So once you get into Mastering Chemistry, you'll see the exact due date. But just know it's got to be done by the time that day arrives. So just pay attention to those 2 columns. The next thing to look at here is our lab schedule. If you have questions about when you should come into lab and what to print off that week and what to do, every name should be listed in the PDF that tells you if you're in group A or group B. That is found on Blackboard in our lab folder, the online classroom tab in our Blackboard course. So check that out. If you cannot find your name, let me know, because everybody needs to know if they're group A or group B, so they know if when to show up or what lab to complete in their, at home on every week. So that is the syllabus. Quizzes will be completed through Blackboard. It'll be an assignment I create through Blackboard. There may be times I use Mastering Chemistry, but I will let you know exactly how to access it, when it will be available, when it is due by, so on and so forth, okay? All right, questions so far on any of that before we jump into our lecture? Feel free to, I'm gonna check the, can I check the chat? How do I check the chat? More chat. Any questions on the chat? Okay. All right. Well, we are going to get going with our first lecture, Chemistry for Health Professionals, you guys. And I know, like I said, this semester looks different. I'm still excited regardless, which is why I always start out this very first lecture with this quote. And here's the deal. Chemistry has a bad reputation, right? This is a chemistry class, and chemistry is not everyone's favorite. So there's that. But I still think there's so much we can learn beyond chemistry. I plan to learn this semester as we go, and I'm going to have a good time with you guys. And so here's the quote I like. It says, "It has been my experience that you can nearly always enjoy things if you make up your mind firmly that you will." So that is what I'm going to do every day that I meet with you guys. I want you guys to also choose to do that as well. But if you find yourself feeling overwhelmed at any point, please reach out to me. And I know things being virtual, I'm going to try to, for you guys to get to know me as best as possible. I'm going to try to get to know you guys as best as possible. It really bums me out that that's going to be harder to do in a virtual setting. But I want to get to know you as much as possible, and I want to make myself approachable so that you can reach out to me. We can set up a Zoom meeting. We can work problems. We'll do whatever we need to do. But if you stay quiet and you're struggling and I don't know you're struggling, I can't help you. And so please let me know any ways that I can help you, and don't wait the day before the exam. So there's that. I also like to start out my lectures, every new lecture, not every day, but every new lecture. So like every new chapter we get into, I post a picture of a hike that we have either gone on or that I want to do. And this one I wanted to start with because it's perhaps the most iconic hike in Arkansas. So if you're new to Arkansas and you like to be outdoors, this is for you. Or if you just have never been hiking, it's all for you guys. This is called Hawksbill Crag, or Whitaker Point is another name it goes by. This hike, it's not very strenuous. It's near the Buffalo River, so it's about an hour-and-a-half drive from Conway. So it would be an all-day or at least an all-afternoon thing if you decided to go, because it's a pretty good hike and then a decent trail. I don't know the exact length of the trail, but it's kind of an out and back, and it takes you to this overlook, okay, this crag as they call it, out into nothingness. So be careful when you get to that point because there are no rails. But it is one of the most beautiful spots. So I highly suggest it when the weather starts to cool off a little bit, September, October, and the trees start to turn colors, really in November. This hike is just, it is beautiful, you guys. You should really do it. So there is the hike for the day. And the next one, this picture is actually going to get us into lecture, but it is another hike. So before I approach it from the chemistry standpoint, the hike that this is showing is the Grand Canyon. So me and my husband got to go for our 1-year anniversary a while back, but this is called Plateau Point. And the trail, I kind of will mark it out in pink here. The trail winds down. You can see it most of the time, but it winds down and it takes you all the way out. Oh, my pencil started my. It takes you all the way out to this plateau right here. And what's really cool about this point is you are halfway down in the canyon and you're halfway out. So you can look down at that point and see the river, the Colorado River that runs through the Grand Canyon. And you just are engulfed by the canyon on all sides. It's really magnificent. So, but then you have to hike all the way back out. So that is called the Bright Angel Trail. I'll write it on there for anybody who wants to know. Bright Angel. And it takes you to Plateau Point at the Grand Canyon. This is on the south rim of the Grand Canyon. Okay, but when you look at this picture, so we're going to get into chemistry mode here. When you look at this picture, you see all kinds of stuff. You see the sky and the clouds. You see different layers of earth that are different colors. You see trees. And all of this falls under the category of matter, okay, which leads us to our first question. What is matter, okay? Matter is, the layman's definition is just matter is stuff. Okay, and I know the pink doesn't necessarily show up great on this picture right now, but it will show up really good on the white, so bear with me. Matter is stuff, okay, anything. We can think of matter in the pictures that I have below as a cheeseburger, and then we'll get into the other two pictures, but it's stuff. There's all kinds of matter. Matter is a very vague, vast term. But if we're going to define it a little more appropriate from a chemistry standpoint, it's anything that has mass and volume. All right, anything that has mass and volume. Now, like I mentioned, a cheeseburger, okay? That may be some of you guys, your favorite kind of matter. I would love to know where your favorite restaurant to get a cheeseburger is at here in Conway or Little Rock. We have some good places. But I want you to know that matter can be really, really, really small, okay? We don't want to box things in here. Matter can be really small. Matter can also be really, really big. So if we're thinking about the scale of matter on the small end, anybody, you can unmute yourself and share, what is the smallest kind of matter you could think of? Smallest kind of matter.
Salt.
What was that?
Salt.
Malt? M-A-L-T?
S-A-L-T. Sorry.
Salt.
My voice
Salt.
is trash right now.
Thank you, Olivia. Salt. Okay, salt is pretty small, but we can go actually a lot smaller. Okay, but you're headed in the right direction. Can anybody think of something smaller than a crystal of salt?
Atoms.
Atoms. I don't know who said it, but that is definitely even better. But we can still go smaller than atoms. Can anybody think of something smaller than an atom?
A cell?
A cell is bigger than an atom. An atom is
An
composed
electron.
of many, many cells. An electron, who said an electron? Because that is
Janelle did.
Janelle. That is almost the best guess I would expect from students. But there's actually one thing smaller than an electron. It's called a quark. Okay, so you spell it Q-U-A-R-K, quark, not a C-O-R-K. And interestingly enough, scientists have actually never measured its mass or volume. So very bizarre that they call it the smallest matter. However, if you Google the word quark, you will see a European cheese, and that is not the kind of matter that the kind of matter we're talking about here. Quark is a subatomic particle. It's the smallest thing we know, but the point I'm trying to make is it's so small we can't even see it with our bare eyes. All right. So that's on the small end. What about the large end? What is the single largest unit of matter we could think of? And if we were in face-to-face instruction, you would not actually see this picture on the right because it's a dead giveaway. This is a star. If you look at this picture, it's called Canis Majoris. This is the single largest unit body of matter in outer space in our universe that we know of. Okay, and it actually shows you. I'm going to turn my screen sideways to kind of make the picture bigger. Will it turn? There it goes. So you can see that our sun is kind of zoomed in right here. Our sun is just a speck compared to Canis Majoris. So it's hard for me to even wrap my mind around how big that is, but it's massive. All right. So all this to say, these pictures are just to help you understand matter is a very vague term that encompasses all kinds of stuff, all kinds of things that have mass and volume. Some of those things are very large and some of those things are very small. But that's what chemistry is. It is the study of matter, okay? Chemistry is the study of matter. So the way we study matters, there's a few different ways. One way we can begin to study matter is we can hold a piece of matter or look at a piece of matter and we can say, okay, what kind of properties does this matter have? So some examples, what do I mean by property? Well, matter has color. So we can assess, we can measure with our eyes what kind of color it has. Matter has size. We can measure its size, and there's many different ways to measure size. Size is kind of a vague word. We could measure the length. We could measure the volume. We could measure the mass, how much it weighs, essentially, how much mass it has. Matter also has a temperature, right? So we can measure the temperature. And then I bet you could think of other properties you could measure. Can anybody think of another kind of property that we could measure on a piece of matter? Type it in the chat or unmute yourself. What would be another kind of way we can measure a property of matter? I'll write one. Density.
Could we do shape?
The weight, yeah, the weight.
Is shape one?
Shape, we could measure the shape. That might also fall into like mass and volume sometimes. But shape could be a thing. Okay, density, here's another one. This is kind of a chemistry word, but we can measure its reactivity. Okay, some types of matter are very reactive. Okay, once you light a firecracker, you get a big reaction. Some kinds of matter are very, what we call inert, and they don't react with anything. And we'll actually look at that in chapter 2. But these are some properties that we can measure with matter. There's all different kinds. There's more than this even, but this is a good list to get us going. So, but not only do we look at properties, we also look at the way matter changes. And in fact, because we live in a very dynamic universe, because our bodies are very dynamic things, it's more beneficial to us as health professionals, as nurses, those of you who are going into dietetics or sports medicine, or I'm sure that we have a range of majors in this course. It's more helpful for us to know how things change. Oftentimes medicine and the way things progress and the way we treat people are based on how our bodies change or how treatments change or how matter changes over time. So there's two dominant ways that matter changes. The first one is there's physical changes and there's chemical changes. Physical and chemical. Now, a physical change, how are they different? A physical change does not alter the chemical makeup of the matter that we have at hand. Oh, texture and melting point. Those were in the chat. If you look there, those are two other properties that we can measure. Yes, thank you guys for that input. Texture and melting point are other kinds of properties. A chemical change does alter chemical makeup, okay? Chemical change does alter the chemical makeup. So to further talk through these kinds of changes and see how they're different, I have some pictures at the bottom of this slide that I want us to talk through. And we're going to label these pictures as chemical or physical changes. So if we're talking about the first one right here, number 1, you see a beaker with quite a bit going on. You see lots of colors. What if you just had to guess, is this a physical or a chemical change? What kind of change would you guess? You can type it in the chat. You could say it.
Would it be physical? Chemical? Just
Okay, we've gotten 3 chemical in the chat. Someone said physical.
I was thinking physical, but I could be wrong.
It's okay. Why do you think physical?
I'm assuming, I don't know, just because like, I don't know what's even in that beaker, just whatever
Yeah,
chemicals.
we don't know what's in it. We don't know what's in it.
Because it made a flame, I don't know, I'm just assuming like, you know, it changed its physical appearance. Like it's a flame now instead of just this liquid.
Right. So if we do change the appearance, I think that we have altered the chemical makeup. If you light something on fire, do you have the same thing after it's been burned that you had before?
Mm-mm.
No, not at all. So anytime you have fire involved or combustion or a flame, that is certainly a chemical change. So I'm going to abbreviate. It's a chemical change there. All right. Let's look at the second beaker. Okay. What do we have going on here? It may be hard for you to tell. I'm going to zoom in. We have a beaker with some stuff and it kind of looks wispy. Sometimes people will say this beaker looks smoky. It's not smoke. Anybody want to type what they think? Is this a chemical or a physical change happening before your eyes? Chemical. I'm getting lots of chemical answers. Here's what I see. If I really zoom in, it looks like this portion of the beaker is like a liquid, maybe even looks like some ice maybe. And then I think this on the top here, like I'm gonna draw an arrow. These things right here to me kind of look like bubbles. And then all this here looks like vapor. That's what it looks like to me. Would anybody else? Okay, I'm getting some answers, physical. So what's happening is I believe here we have a liquid. And then I believe, out here we have a vapor. So liquid to gas, this is a physical change, okay? And we're gonna talk through that a little more deeply in a second. Anytime you change from a solid to a liquid to gas, or vice versa, any of those directions, we have a physical change. Okay, so this is just evaporation.
Can I ask a question?
Yes.
How is it like a physical change? Like, because you can't go back from gas to liquid, right?
Yeah, you can. What do we call that process? A gas to a liquid.
Oh.
What do we call it? Anybody know? Condensation.
Condensation.
So if something, I mean, you've seen like if you are in, oh, what's a good example? Kind of like when your goggles fog up,
Yeah.
you're getting condensation on your goggles, or if you are in a car and you turn the heat on really high and you have a difference of hot and cold on the outside and the inside, you'll see condensation form like on the windows.
Okay. Oh,
Thought
okay.
I was crazy for thinking condensation. You were not, okay?
Okay.
Condensation. So that's going back from a gas to a liquid. So anytime you're changing from a solid to a liquid to a gas, you're not changing the chemical substance. You're just changing how far apart the molecules are spaced. And we're actually going to draw pictures of that in a second. So that's a physical change. Number 3, we have a yellow powder. And this is kind of a static photo, so it's hard to imagine like what's happening. But if you formed a yellow powder from, say, a clear solution, or you had a color change of any kind, if something changes colors, that is a key indication that what you have is a chemical change. So this would be representative of a chemical change if you see something change colors. Okay, lastly, in this picture, number 4, if you have a piece of metal and you grind it down into shavings, like what we see, would you consider that to be chemical or physical? Physical.
Physical.
Physical. I'm looking at the chat. Physical, all physical. That you guys are right. Okay, we're just breaking it apart. We're not changing the chemical makeup. We're just breaking it into smaller pieces. Okay, so I will tell you this for exam 1, which is not anytime soon, but I want you to be able to tell me the difference or identify the difference on a multiple choice question, or if I ask you to write about it, tell me the difference, or maybe even give me examples between chemical and physical changes. Okay, so for sure know how to tell me the difference between these two. Now, another property that we did not mention earlier is state of matter. And we kind of with square number 2 or picture number 2, we were talking about the difference between liquid gas changes. A state of matter, it's either solid, liquid, or gas. Those are the possible states of matter. Now, yes, there is a 4th state of matter, plasma. That's beyond the scope of this course. We don't need to get into plasma. So we're just mostly going to focus on solid, liquid, and gases, okay? So any changes, as I have mentioned, between solid to liquid, vice versa, liquid to gas, vice versa, these are physical. These are physical changes, all right? The easiest analogy for me to explain this to you with is using water, okay? Water is a type of matter. It can take on any of these 3 different forms. In fact, most compounds or elements can be in a solid, liquid, or gas state. On planet Earth, water is naturally found as a liquid, but there are environments where we know it changes to a solid or gas. So how are these states of matter different? Let's briefly talk through that, and then we're going to get into the changes a little more. If we're talking about water, as a solid, we know that we call it ice, okay? But solids, they have a definite volume and a definite shape, okay? They do not depend on the shape of their container. They're independent of that. But liquid is different, okay? We know liquid water takes on the shape of its container. So it's got a different shape if you put it in a bowl, or if you put it in your water bottle, or if you pour it out on the floor, which my 2-year-old likes to do with her drinks. But it has a definite volume, a variable shape. Okay, there's a certain amount of it, but it can be in whatever shape depending on the container it's in. Okay, so that's one way liquids and solids are different. Gas, okay, when we're talking about water, we call that steam, but gas has a variable volume and shape. So the shape and the volume can change. Gas could be forced into a really small container. That's called compressed gas. There's like compressed gas tanks that you might see sometimes, like in a research lab or in a hospital. That's gas that's at a really high pressure, like a helium tank. Okay, if you've ever blown up a balloon with a helium tank, there's a bunch of helium gas pressed into that small space. But gas can also, it'll fill the size of the room. So the room I'm sitting in now, there's a certain amount of gas in it. It'll fill the room or whatever container it's in. So it does not have it does not depend It has a variable volume and shape. That's what I'm trying to say. Okay. On this next slide, I want to draw what's happening though. If we think about water as molecules, individual molecules, how as a solid, liquid, and gas are the molecules behaving differently? So let's draw this out. I'm going to draw some pictures for a solid water molecules in solid form, water molecules in liquid form, and water molecules in a gas form. In a solid, molecules, and not just for water, for anything in a solid state, the atoms or the molecules are closely packed together. They might look like this, okay? We're going to draw them really close together. Usually they have a very organized arrangement, okay? They're interacting with each other a lot, and they're not moving a whole lot. So they have very little movement. And lots of interactions. These molecules are interacting. They're close together. We could say they're close together. So that's some things to note about molecules in a solid state. As a liquid, let me draw a different picture. The molecules, they can move about freely. We know liquids are, we use the word fluid. Okay, so I'm going to draw some arrows to indicate that these molecules are moving more than they are as a solid. And if you'll notice, they're a little further apart. Okay, so they're further apart. And they, I'm going to write more movement, fluid, and less interaction between the molecules. Now, as a gas, molecules have the highest amount of movement and energy, okay? So if we have a gas molecule of water, I'm going to put a little double arrow to indicate it's moving really fast. And I'm going to draw these molecules very spread out, okay? So they're zooming past each other like they're on the interstate. Okay, so these are the furthest apart. And these have no interaction. They don't have time to stop and chat. All right. So just to give you an idea why solids and liquids and gases have the characteristics they do that we underlined up here regarding their volume and their shape, it's because of what the molecules are doing, okay? And how they're interacting or not interacting and the amount of energy that they have, okay? All right, questions so far on this stuff? All right. Now we're going to continue our talk with water. I'm going to show you two pictures because I want to look at, we've talked about how water changes through physical changes from a solid liquid to a gas, but we can also, water can undergo a chemical change just the same way it can undergo a physical change. So we have two pictures here, this kind of coffee pot looking picture on the left, and then something that looks a lot more complex on the right. On the left, this is the way water can physically change, and we've already seen a picture of that, okay? We have liquid on the bottom, and we have gas on the top. And this is just a change of state. When I say state, I mean solid, liquid, or gas. So this is why it's just a physical change. If we look at this chemical reaction that's written down below here, we start out with liquid water. And anytime you see an L like this in parentheses after your chemical compound, that just denotes that it's in a liquid form. Okay, so we have water as a liquid. If we follow the arrow over to the picture that says physical change, we've denoted now that we have H2O, water, as a gas, okay? The abbreviation G indicates that it's in a gas state of form. And that's what you see in the picture. Now we have common names for this. In fact, we wrote the common name for this exact change earlier, evaporation, or you might call it boiling. I'll put in parentheses boiling. we also have common names for the other changes of state, right? So if we were going to take water and go from a liquid to a solid, liquid water to solid water, what would you call that change? What's the common name for that kind of change? You can type it or say it.
Freezing.
Freezing.
Ice.
It would be ice at the end, but the actual change, we call that freezing. What if we go from a solid to a liquid? What do you call that? That change.
Melting.
Melting. Yes, melting. Okay, and then we also mentioned condensation earlier as another one. Okay, these are all state of matter changes. So if you were to see these words on an exam, I would want you to be able to identify those as a physical change. All right, these are all physical changes because they're just a change. We have not changed the fact that it's actually water. We've just changed what state of matter it is. Okay. Now let's look at the way that matter, and here we're talking about water, can undergo a chemical change. So if we have liquid water, which is what you see in this beaker, I'm going to kind of circle it and or box it in pink here. In this beaker, we have liquid water. And what you see in the background, I'm going to square this. This is kind of some sort of battery pack. And it looks like we have these wires hinged to some sort of piece of metal. What we're doing is we're running an electric current. Okay, we have it written out in word form down here. We're going to pump an electric current through water. And when you do that, what happens? What do you see in the picture up here in these test tubes? What do you see here?
Bubbles.
Is it heating it
Bubbles.
up?
Boiling.
It probably is heating up a little bit. But what we're doing is the reason this is a chemical change is we no longer have water after we run an electric current through it. We have created two products, hydrogen and oxygen. You guys are familiar with hydrogen and oxygen. In their natural state, as they exist on planet Earth, you see this little G right here, they're both gases, okay? So hydrogen and oxygen, they're both gas. So we're creating gas. And we know gas bubbles like to escape from liquid, all right? And that's what you see here in these test tubes. So when you see any sort of vigorous bubbling or fizzing like this, that's an indication that you have a chemical change. And more importantly, the reason this is a chemical change is because we no longer have water. And remember, the definition of a chemical change was that it does alter anytime matter is altered to where it no longer has the same chemical composition. Okay, a chemical change alters the composition. And here we had H2O. Now we have H separate and O separate. So we no longer have water. Now we just have two gases. And we see that in the form of bubbles coming out of the water. Okay. Questions on the difference here between physical and chemical changes. I'm going to give you another example, but any questions first? You can type it in the chat. Feel free to ask it if you want to. All right. Here's another picture. You guys are familiar with lighters. I love to light candles at my house. We grill. I hate these kinds of lighters. Anybody with me? Because you always like end up burning the crap out of my thumb. Okay. I like the ones with the trigger and the long, the flame is far away from my hands when I light it. But here we have a lighter, and inside the lighter, I'm going to circle, we have these molecules. Now, obviously, these are not molecules you can see with the naked eye, but I put them there just for emphasis in this picture. This is a molecule of lighter fluid, and this is butane. Okay. You might have heard of different kinds of fuels, methane, butane, propane. Butane is the common one in lighter fluid. So it's made up of carbon, and carbon is the dark gray spheres in that molecule, and it's also got hydrogen in it. And hydrogen are the white spheres that you see in the molecule. Now, we have said the picture on the left is a physical change. Okay, in the lighter, this is liquid butane. Okay, we can see that it's liquid. But this lighter has an opening, and it's a slow process, but over time, these liquid molecules escape and they vaporize. Okay, so up here, we have butane, oops, and it's a gas. So the reason this is physical is because look, the shape of the molecule, the fact that we have white and black spheres, and they look about the same size, the molecule here is no different from the molecules down here. They're just more spread apart. One's a liquid, one's a gas. So this is why this is a physical change. We have not altered the chemical makeup of butane. Same number of black and white spheres, right? Well, if we look at the picture on the right, we have a chemical change. That's how we've described this. Why is that? Well, down here, we still have liquid butane, but does it look like we have liquid butane up here in the flame? No, we have red spheres. Where did the red spheres come from? Anybody know what the red is or have a guess?
The fire, like it
Okay.
heating up.
We do have fire going on, okay, which is indication when you strike a lighter, you are forcing oxygen to react with the butane, okay? So butane is a carbohydrate, it's a fuel. When you react it with oxygen, you get what we call a combustion reaction. And you don't have to know that fancy word right now. We'll get into that later. But we are reacting it with oxygen, and that's what these red spheres are, is oxygen atoms. And when they react, they create two new things. Any combustion reaction is going to give you CO2. That's what this molecule is right here, because carbon is the black or the dark sphere. Oxygen is the red. So we have a carbon and two oxygens, and you're going to get water. Okay, so hydrogen, and that's this molecule. Sometimes it doesn't want. That's that molecule I just circled, where hydrogen are the two white spheres, and oxygen again is the red. So we have two different products. As we go from liquid butane down here up to here, we have different products. We have altered the chemical makeup of our reactants. We no longer have the same thing. That's why this is a chemical reaction, okay? Questions on that? All right. Well, so we're gonna do a poll really quick. I'm gonna turn my screen so you can see this a little better. And that's actually one feature about Zoom that I really like, because I never used clickers in class, but there's certain things you can do. So I'm going to launch a poll. You should see this little screen show up. And I want you to look at figures A, B, and C on this slide. And then I want you to tell me whether A, B, or C represent a chemical or physical change. And this is not timed, but I'm going to go ahead and launch this poll. Okay, I've launched it. So you should see a little screen show up. And it asks you questions 1, 2, and 3. Does figure A, figure B, figure C represent a physical or chemical change? And I'll show the results at the end. So I'm just going to give it a minute. Look at them. Tell me what you think. If you grab the little top of the window, you can move it, because some people were saying that it's in the middle of their screen. So grab the little top bar and you can move the poll screen if you need to see the pictures. I'm going to give you all some more time. No rush. Got about 51 of 64 have answered. So we'll give another couple seconds for those last of you guys to put your answers in. Almost there. 96% have voted. 2 more people. Go ahead and get your answers in. You got a 50-50 shot. All right, we're 100%. Okay, I'm going to end the poll and I'm going to share the results. Okay, so let's look at these. You should be able to see the results. 5% or 8%, sorry, about 5 of you voted chemical on A. So let's look at A. The rest of you voted physical. So if we're looking at A, on the left side, these are our reactants. And on the right side is the product. So if we look at A, I see, if I'm looking at one molecule, I see some black, I see about 5 or 6 white spheres and 1 red. And if I look at one molecule on the product side, I see the same thing. The molecule to me looks the same. All of them do. It's just that on the reactant side, they're closer together. On the product side, they're a little more spread out. They're spread out, but it's the same molecule. okay? Now, because of that, this is a physical change, okay? We have not altered the chemical composition or the chemical makeup of this molecule. We have the same thing, the same molecule on the product side that we do on the reactant side. So if you wrote physical, you were right. Now let's look at B, okay? B, I noticed that I have some molecules that are 2 red spheres, other molecules that are black and white. But on the product side, I don't have any molecules that are totally red, and I don't have any molecules that are totally black and white. I have black and red, and I have white and red. So to me, that tells me I have new molecules on my product side. So this has got to be, if I have new molecules, that means the chemical composition is different, and this is a chemical change. Any questions on that? Okay, most everybody voted chemical. Number 3, most of you all said physical. So let's look at that. These look like water molecules to me, and you don't have to know that, but it's red and white, and they're all close together. Here we have red with 2 white spheres. They're just more spread out. So again, that matches exactly what's going on in A. These are same molecule, just spread out. So this is definitely a physical change. We have not altered the composition of the molecule or the makeup. Questions on identifying physical and chemical changes? Okay. I am going to, I have one more poll that we're going to do. So I'm going to go ahead and launch this. So read this question. It says, which of the following represents a physical change? Just to kind of reinforce what we've been talking about. You have 4 options here. One of them is physical. Roasting a marshmallow, stirring sugar into a gallon of hot tea, some iron tool left out and it gets rusted, expired milk turns sour. Which one of those is physical? Only one is physical. Remember, if you're creating something new, it's probably not a physical change. This one's really interesting. We're getting different answers. Pretty evenly across the board. Okay, we've got about 3 people left to answer. Go ahead and get your answers in. One more person. Just take a stab at it, even if you don't know. Waiting. 63 of 64. All right, I'm going to end it. Okay, I'm going to share the results. So y'all will be able to see what the right answer was. But we got some different answers here. So the right answer is the one in red. Stirring sugar into a gallon of hot tea. That is a physical change. Looks like we need to talk about why the others are not physical changes. So let's start with roasting a marshmallow. Does anybody want to try to explain why that would not be a physical change? Anybody feel confident in that? Well, to me, the key word here is roasting. Okay, if I say roasting, you should understand that there's some kind of heat or fire involved. Okay. So if we're grilling, if we're roasting, if we're using fire, remember fire changes things, all right? So when I'm roasting marshmallow, if I roast it hardcore, you're gonna see this black stuff show up on the outside, or maybe you don't like to roast your marshmallow very hard, but you see the outside of the marshmallow changing, okay? So maybe some ash showing up on there. You're creating a new substance for sure because you're reacting it with the fire. So that is a chemical change occurring, all right? And stirring sugar into a gallon of hot tea. Why is this physical? Why is it not chemical? Well, the sugar, let's say I have a sugar crystal about this big and I drop it into my hot tea. What's gonna happen to that sugar cube or crystal?
Dissolve.
It will dissolve, okay? What does the word dissolve mean? All it means is that the sugar molecules, a sugar cube probably has millions of sugar molecules. Okay, molecules are really small. A sugar cube contains thousands, if not millions of them. All it means is we're breaking that cube apart into smaller pieces, and those sugar molecules are just spreading out throughout the tea so that every drink tastes the same. It tastes sweet. So have we actually changed the makeup of the sugar molecule? No, we've just broken it apart into individual pieces or individual molecules. All right. So dissolving something is a physical change. It's not chemical. We have not altered the sugar molecules. We just spread them out inside the gallon of tea. Okay, an iron tool getting rusty. Rust is a whole new compound, okay? You can hold a piece of rust. You could flake it off of the tool, right? If you ever use those like SOS or Brillo pads to clean your dishes sometimes, if you leave it in the water, you notice that it gets rusty, okay? You're actually creating rust, okay? Just another example. And it's a brand new compound. It's a new molecule. So it's different from iron. Iron and rust are two different things. So that is why an iron tool getting rusty, that's a chemical change. And then expired milk turning sour. We've all at some point in our life taken a drink right out of the jug, or it's just gross when you drink sour milk. But if something tastes different, that means there's a molecule or a substance in there that was not there before. So we have a brand new substance we created that is changing the taste of our milk. And to me, and that is evidence of a chemical change. We created something new, okay? We altered the chemical makeup of that milk. And now we have a totally new substance that's accounting for the sour taste of milk. Questions on that? I'm gonna stop sharing this. But because there was a variety of results, I definitely anticipate any questions.
I have a question.
Yes.
So, did you say earlier that if something is involved with fire, we can pretty much count it as a chemical change?
Yes, but there's one really good example that I want to mention.
Okay.
Let's say we're lighting a candle. What do you notice happens to the wax?
Melts.
The wax just melts. It goes from solid to liquid. So from that regard, even though there's a flame involved, all we're doing is melting the wax. But we are burning the wick. So if you're talking about something like burning a candle from the standpoint of the wick, that's a chemical change. You see the wick it was white initially and now it's black after you burn it. But if you're talking about this from the standpoint of burning a candle, you're just melting wax. So you have a physical and a chemical change going on at the same time, even though fire is involved. So I'm not going to try to split hairs like that, say for an exam question, but that is an example that I always think of. Even though fire is involved, from one standpoint, it's a physical change. From the other standpoint, it's chemical. Does that make sense? Does that help? Okay. Can y'all still? Am I still screen mirroring? Yes. Can y'all see? Is the screen moving or is it staying the same? Like, can you see me scrolling through the slides?
Staying
No,
the same.
it's staying the same.
It seems to appear stuck. So I'm going to stop sharing for just a second and try to reshare because it's not catching up with what I'm doing. Let me try again.
Yeah.
Okay, now, all right, there we go. So we're going to move on with the amount of time we have left. We just have a few slides left. We're going to identify 4 signals or signs of a chemical change because sometimes chemistry is really sneaky and a chemical change can be happening and we don't recognize it. So there's 4 key signs, visual signs or tactile signs that let us know a chemical change is occurring. So let's look at this first one. I'm going to turn my screen sideways to make it bigger. So let's look at chemical reactions. Right here, this first one, we have a reaction. We actually looked at this earlier. This is water running an electric current through it, and we get hydrogen and oxygen. So anytime you write a chemical reaction, on the left side is your reactants. On the right side is your products, okay? So here we have water as the reactant, hydrogen, oxygen are the products, and we see that the change that's occurring, we always draw an arrow from left to right. We're applying a electric current. Now, what sign here, what visual sign did we see earlier when we talked about this that let us know a chemical change was happening? Anybody remember? It was the picture with the electrode and the two test tubes of water on top.
Bubbles.
Gas bubbles, okay? Now, why do we get gas bubbles? Well, let's think about the products we're making. Hydrogen and oxygen, what do you know about those? In their natural elemental state, what is hydrogen and oxygen? Are they a solid, liquid, or a gas?
They're gases.
They're gases. And so when we're creating gases, they like to escape from liquid, and we see that as gas bubbles. So anytime you see gas bubbles, oops, just one S. This is sign of a chemical change. Okay, that is one of the signs of a chemical change. And I'm not talking about you dropped a penny in some water and it splashed and it made a bubble. I'm talking about like vigorous bubbling. Okay, sometimes even fizzing. Now, somebody asked me a question from the first lecture that was really great. And they said, well, what about when you open a can of soda and then after a while it goes flat? Is that a chemical or a physical change? What do y'all think?
I kind of feel like it's neither.
Physical? No.
I think it's physical just because it goes right back to its original state.
Yeah, we're not changing the gas. We know CO2 is the gas that's in any soda. Carbonated drinks, okay, contain CO2. Those CO2, it's gas in the liquid, and then it's still CO2 when it escapes from the liquid. So we're not changing the CO2. It's just in one form, it's trapped in liquid. In another form, it's a gas completely. And so that's a physical change, not chemical. But anytime you see gas bubbles forming in here, we recognize we're making new products. We no longer have water. Now we have hydrogen and oxygen. That is a chemical change. And gas bubbles are usually an indication of that. Okay, let's look at the second example. We have nickel, which is a metal, and we have hydrochloric acid, which is a liquid. Okay. Here is the abbreviated reaction. Ni is the abbreviation for nickel, HCl, the abbreviation for hydrochloric acid, and then our arrow pointing over to our products. So we get this product right here, nickel chloride, nickel 2 chloride, and we get hydrogen. Okay, there they are. What sign is going to tell us that a chemical change is occurring? Well, you probably don't know a whole lot about nickel, but I'll tell you, nickel, when it's combined with different things, it likes to form substances that are green in color. So this substance right here is green. Okay, we don't have anything that, even though the text is green over on this side of the slide, don't let that throw you off. None of these things over here are actually green, but we created a product that's green. So what did we get?
A color change?
Yes, a color change. That's another sign that a chemical change is occurring. And then there's actually another sign that goes with this. Can anybody guess the other sign?
That goes with color change?
No, but just that goes with this reaction, number 2. What other product do we create?
Reactivity.
Not reactivity. That's a property we can measure. Look at the other product we create. We create nickel 2 chloride. What about this? The one I'm circling, hydrogen.
That's a gas.
It's
Yeah.
a gas.
A different, yeah.
We should see gas bubbles with this as well because we're creating a gas. So that's not a new sign, but that's one that's also occurring with this reaction. So far we've covered 2 that you may remember. So the 4 signs here, I'm going to write them out. 1 is a color change. 2, I can hear some. Make sure you're muted real quick if you're not. Gas bubbles. Okay, now let's talk about signs 3 and 4. So if anybody remembers from earlier, when I talked about a flame, anytime you have a temperature change, something gets hot or something gets cold, that is evidence of a chemical change. If you put 2 room temperature things together and they get really, really hot, that a chemical change has occurred. You no longer have the same substances. You have you created something new. Or vice versa if it gets really, really cold. Lastly, we call it formation of a precipitate. Okay, that is evidence of a chemical change. Now, this is a fancy word, precipitate. It's a very chemistry word. What do I mean when I say a precipitate? Anybody know? Can't
Like a
see the chat.
byproduct.
It is a product that we create. Gas bubbles.
Could it be like condensation?
No, it can't be condensation, and here's why. A precipitate is a solid. Also, I'm looking at the chat. Someone asked earlier, hydrogen, oxygen separated. Yes, hydrogen and oxygen were separated. To Bailey, who asked that question. Formation of, so a precipitate is a solid, simply put. So that's why it can't be condensation, because condensation deals with a gas going to a liquid. But anytime you form a solid, so let's say we have a test tube here, okay, and we dump some liquids in it, all right? So we have this test tube, we put some liquid in it. Well, if all of a sudden I start seeing some solid particles show up, it might make that liquid look very cloudy. Eventually it might settle to the bottom and we have a layer of solid on the bottom. It might change the color of our solution from transparent clear to a certain color. That is evidence that we have a precipitate forming. It usually is happening in solution, okay? So that's what I mean. Anytime you form a solid and you didn't have a solid before, you have a chemical change going on because you created something new. That solid substance is a new molecule. We changed the composition. All right, questions on the 4 signs of a chemical change? I definitely want you to know these for exam 1. Okay, I think we have just a little over 10 minutes left, so we're gonna go ahead and finish up. We got this slide, and this topic is really the last one. All right, so we're gonna kind of start looking at the periodic table a little bit, and then we'll get more into this with chapter 2. But what you see, and this should, what we talk about now and the rest of this lecture should be reviewed from, say, a high school chemistry class. You should have looked at the periodic table and be at least a little bit familiar with it. But on the periodic table, we have 118 elements, most of which exist naturally on our planet. Some of those elements, though, only exist because scientists have created them, interestingly enough. I've also boxed in several key elements that should maybe be familiar to you guys, especially those of you headed to like nursing school. You may need to know about these elements over here: sodium, magnesium, potassium, calcium, things that our body needs. Dietetics people, you should be familiar with hydrogen. Okay, it's a part of our atmosphere. Carbon, nitrogen, oxygen. Okay, these are organic molecules that our body is composed largely of carbon. And then also we have some others boxed in, but these here, as you see them, these are all elements on the periodic table. And elements are represented by what we call chemical symbols. All right, so how do you write out correctly a chemical symbol for any element? Well, you'll notice some elements have 1 letter, some elements have 2 letters. So just real quick, let's differentiate. If I have a single letter chemical symbol, it needs to be capitalized. Wait. Capital sepia. I'm having issues here. Capitalized. Help me spell it. Is that right? Capitalized? That looks right. We're going to go with that. Okay, 2 letter symbols. The first letter is capitalized. I'm going to abbreviate. Second letter is lowercase. All right, so for example, do not write sodium, which is Na. You wouldn't write sodium like this. That's incorrect. You would write the first letter N capitalized, second letter lowercase. Okay. All right, now let's talk about compounds. So that's elements. Compounds, first off, how are compounds different than an element? Well, a compound is the combination of 2 or more elements, okay? So compounds is the combination of 2 or more elements. All right. So I've shown some different examples of compounds over here on the right side, and we represent compounds by chemical formulas. So water, H2O, that's a compound, and there's its chemical formula, H2O. And that tells us that there are 2 hydrogen atoms and 1 oxygen atom. The next one down, anybody know what CH4 is? It's another compound. It's a type of fuel. It's methane. We have 1 carbon atom involved, 4 hydrogen atoms. Who knows what this last one is? It looks really complex. C12H22O11. Anybody know? We eat it a lot. This is sucrose. Okay, so it tells you how many of each kind of atom. But these are all chemical formulas, and this is how we express compounds. So let's write out 2 quick rules for writing out chemical formulas. First off, formulas contain letters and numbers. Secondly, all numbers are written as subscripts. Okay, and remember, a subscript is the number, it occurs after the letter it's referring to. It's a little bit smaller and written lower down. Okay, so that's why all these numbers are a little bit lower than those letters, and they're smaller. So write them as subscripts, except the number 1. If you'll look up here with like water and methane, we only have 1 oxygen atom, so we do not have to put a 1 right here. We don't do that. Just writing the O indicates that there's 1. Same for carbon. We just have 1 carbon atom, so we do not put a 1 right there. We just write C. Okay, so those are some general rules you just might want to review. I'm not going to quiz you on an exam on the exact rules. Like, tell me the rules. I want you to be able to write them, okay? Lastly, I'm going to point out this table down here. We will not use the Latin names. So some elements, you might, if you were to look it up on the internet, if you're trying to Google something for our class, you might see these Latin names, but we're not going to use it. I just want you to know that some elements, people refer to them via their Latin name, like copper, cuprum, ferrum for iron, things like that. And we're mostly, though, going to use the modern names. That's what's going to be in your textbook, and that's what we're going to use in this class. But just don't be confused if you're on the internet or something and you see the Latin names. Those are still a method of communication in chemistry for certain elements. Okay, questions on how to write out chemical symbols and chemical formulas. Definitely want you to be able to do that. Tell me the difference between the two. Write an appropriate one, so on and so forth. Questions there?
No, ma'am.
Okay. Lastly, in the time we have left, we are going to go over this table, and I'm going to turn this so we can see it better. So we started out this lecture talking about matter, and we said matter is a very vague word that describes all kinds of things. It's just stuff. Everything has, anything that has mass and volume is matter. But because it's such a vague word, and there's so much matter in our world and in our bodies and things that we deal with, we have to have ways of classifying it so that we can better study it and understand it. So if we have a type of matter and we want to classify it or know more about it, we will ask questions like this. The first question we would ask, or we should ask, is does it have a variable composition or a uniform composition? Okay, what's the composition? Is it varied or is it uniform? If it is uniform, and what do I mean by composition? I mean, what makes up that matter at the molecular level? What kind of molecule or element or what kind of substance is it? So if the matter does not have a variable composition, so the answer there is no. Well, that means the composition is uniform. And what we're dealing with, we call a pure substance, okay? From there, we have 2 types of pure substances. So another question we might ask is, can we separate it into simpler substances? If the answer, again, is no, we have an element, okay? Here's an example. What's inside any balloon here, the Goodyear balloon? Helium. Helium is an element, okay? So anything that is on the periodic table, that is the simplest kind of matter we have. We cannot break it down any further. All the atoms are the same. And again, here, helium is our example. And if you look at the picture, this box right here, you'll notice all the particles in that box, they're the same color, they're the same size. You may think some of these look a little like faded like this. It's just trying to show you depth. Like some of them are far away and some of them are close up. Just trying to look 3D. But all of them are these green spheres, okay? Now, if we have a pure substance and we can separate it into simpler substances, then what we have, the kind of matter we have, is a compound. The example that we've used actually a lot in lecture today is pure water. So if we look at this box, pure water is our compound. All the molecules, and I say molecule here or compound because it's made up of more than one type of element. We have oxygen and hydrogen in water. But if you'll notice, all these molecules, they're the exact same. They have one red sphere, two white spheres. They're all the same, okay? So this is a pure substance. Water is the only thing in this glass, but it's a compound because it's more than one element, okay? If we go back up to the top of this chart, okay, let's say we ask the question again. We have matter. Does it have a variable composition? Yes, it does. If the answer is yes, then what we have is a mixture, okay? And then we have two types of mixtures. If the mixture is uniform throughout, if it is, then what we call that a homogeneous or a homogeneous mixture. An example here would be like if we put these sugar cubes into this tea, we have sweet tea. Every sip will taste the same because all the sugar molecules are dispersed evenly throughout that cup of tea. My favorite example, if you watched the intro video that I sent earlier this week, I love ice cream. So vanilla ice cream is a homogeneous mixture. Why? Well, what's in ice cream? A lot of things are in ice cream. So a lot of things are in mixtures. We have fats in ice cream. We have sugar in ice cream. We have air. We have water in the form of ice in ice cream. All these things mixed together, but every bite of a good vanilla ice cream should taste the same because all of those molecules are evenly spread out. Okay, they're uniform throughout the mixture, and that is a homogeneous mixture. So if you look at this tea at the molecular level, okay, these big blue molecules are probably the sugar molecules, and you have all these water molecules, but all the sugar molecules are evenly spread throughout the tea, okay? If this mixture does not have a uniform composition, so no, it does not, we call that a heterogeneous mixture. Here, the example is wet sand. If you scoop up in a bucket or a shovel, if you're at the beach, so many people have been going to the beach this summer. Not jealous, okay? But if you were to scoop that up, you're not going to have things evenly mixed. You might have a layer of water on top, which is like what you see on the top part of this, and then you might have a ton of sand on the bottom, okay? Down here, this is all sand, okay? And up here, this is all water. And things are just not, they're not uniform throughout. So we call that a heterogeneous mixture. Other examples of a heterogeneous mixture would be, say, vegetable soup. If you throw a bunch of Oreos in your ice cream, now every bite's not going to be the same. You might get a big bite of Oreo, and then you might get a bite of just ice cream, okay? So anything where the mixture is not uniform, that's a heterogeneous mixture. Anything where the mixture is uniform, that's a homogeneous mixture. Questions on how we classify matter. I definitely, on exam 1, want you to be able to tell me the difference between an element, a compound, a heterogeneous, and a homogeneous mixture. Question, can you tell the wet sand is heterogeneous because the water can separate? Yes, because you have the water and the sand are not evenly mixed, okay?
I have a question. It's not necessarily like how to do this, but are you, I don't know if you're going to, but are you able to like take this chart and like put it in Blackboard for us to like have to look at?
It's in Blackboard. Yeah, if you download,
Okay, it is.
if you download the lecture in our lecture folder titled Matter in Chemistry, this is the last slide of that lecture.
Okay. And also, are you like, do you want us to like comment our name or anything for attendance? I don't.
Oh no, Zoom automatically collects it for me.
I just wanted to make sure. But
Yes, yep, you don't have to write your name or anything. So in our last minute here, I'm just going to do a recap. I want you to have known one, how to classify matter, know the differences between element, compound, and our two types of mixture, and then 2, the difference, I'm going to abbreviate, the difference between chemical and physical changes. And specifically with chemical changes, know the 4 signs. Okay. Lastly, and I know we're at time, but this is a table of ionic or polyatomic ions. We'll get into this with chapter 3, but for exam 1, because these will show up on a quiz or 2 before exam 1. They won't show up on our first quiz, but starting with quiz 2, these are fair game. I'm going to circle 11 of these that you need to memorize. And when I say you need to memorize, you need to know both the name and the formula, okay? So start now. This will help with exam 1. So the first 5 in this column, I want you to memorize those. And for this one down here, just call it the bicarb ion, okay? You don't have to call it hydrogen carbonate ion, just call it bicarb, okay? So know these 5 and also the hydroxide ion. So there's 6 on this first column. And again, this is all recorded. So if you didn't get all this written down right now, this will be recorded. You can find it in Blackboard later. I'm going to slide over to the next column. I want you to know nitrate and nitrite, phosphate, and then 2 more. Sulfate, and down here at the bottom, sulfite. Okay, that makes 11 total. So start working on these 11 polyatomic ions. I may ask you to tell me the formula if I give you the name. I may give you the formula and ask you to tell me the name on a quiz, so on and so forth. So, well, we are a minute past time. I apologize. If you have any questions, I will stay on and answer questions. If not, we're done with lecture. You can hop off. Thank you for joining us, and I'll see you guys next week in lab.
Hey, I had a question.
Yes. Who's talking,
Okay,
by the way?
this is Janelle Aldita Wood.
Okay.
So you said all of this is also on where is it at exactly? I'm so sorry.
It's okay. If you go to Blackboard, so I'm going to actually stop screen sharing with my iPad. I'm going to switch over to my computer, and I'll tell you exactly how to get there via Blackboard, okay? Hold on just
Okay.
1 minute. So we're
And
gonna,
I was having trouble with my laptop, and I could hear you, but my screen went black. And then I just turned it off because I couldn't see anything, and I couldn't like ask any questions or anything.
that ever
So-
happens, I just encourage you to totally log off the Zoom and then try to get back on. Sometimes there's glitches. But again, these are all recorded, so you'll be able to watch the lecture and see me and hear me and everything. So I'm gonna stop screen sharing with my iPad really quick. And now you guys can see me. Now I'm gonna screen share just with my desktop. Okay, let's go here. Okay, so can you see our Blackboard course? Can y'all see that, my screen?
Yes.
Okay, so if you're in our Blackboard course, then over here on the left side of the page is where everything is. So if you go, you were asking where the lectures are, correct?
Yeah, the recorded ones.
I haven't posted any recorded ones yet. I'll have to make a new folder of that. But if you go to the online classroom, that is where I will post them. Here in lectures, so far, I've just posted all the PowerPoint files. And what I'm going to do is I'm going to add more content underneath this. That will be our lecture recordings, okay? So you'll come into here. I haven't posted any yet because this is the first day we've recorded any. But once I get those from Zoom, I'm going to download them. And what I may do is I may break them up into 10-minute portions because it's just a lot to stream an hour-long video. So we'll see. I don't know. I may try to post the whole thing. I may break it up. We'll see what's easier. But you will find them here in the lectures folder on Blackboard. Does that help?
Yes, thank you.
Okay. Any other questions? That was a great question. Well, there's only 7 of us, so I think everybody is good. Any other questions, though, shoot me an email. I'm happy to answer. And I will see you guys next week. Thanks for joining.